Okay, the next problem gives us the population that begins with 25,000. It says continuous, so we're going to use that formula, which is A equals P e to the RT or KT. And this P is the amount you start with, which is 25,000. E to the, in the rate, right here, K is 0.0166 times T. So there's our function that goes right there for population. Okay, next problem gives us the ratio of carbon-14 to carbon-12 formula, which is an exponential formula. That's related to, the ratio is related to the time that an organism has been dead for. So you could type in, if you know the ratio, which they give us in this case, you can find out how long that specific organism, this specific organism has been dead. So plug it in, 0.72 times 10 to the negative 12 equals 1 over 10 to the 12 times e to the negative t over 8,223. So we're going to multiply both sides by 10 to the 12 to get rid of that. We're going to take the natural log of both sides. And this gives us negative t over 8,223. We're going to multiply both sides by a negative 8,223. So that cancels the negative and the bottom over here. So our time is this value right here, which we're going to plug into our calculator, and that gives us 2,701.29 years. I'm not sure how they want this in here. It might be a whole number. It says approximately, so it might just be the whole number is good enough. Okay, the next problem says we have this formula here. This is it wants the half-life. Well, if this is our exponential formula, it looks like we start with 1 there, because we have our equation is y equals, in this case, p e to the RT, basically. So we start with p, which in this case is 1, or in this formula. We have the rate right there. So basically we want to know when we have half of that amount left. So plug in 1/2. 0.0001 t. So basically, we start with 1 right there. When do we have half that amount? Well, I'm going to take the natural log of both sides. So that brings us down. So the natural log of 1/2 equals negative 0.00001 t. Divide both sides by negative 0.00001. And that gives me a time of about 69,314.7 years. Okay, the next problem then says find the half-life of an element that decays this amount per day. So we're using our same exponential equation. The rate they give us is 1 minus this 3.4%, which is 0.03403. And we want to know when there's half the amount remaining. So that would be, we'd solve for this t. You can divide the a out, and you get this 0.96597 if you do 1 minus this. Raised to the t power. Now change that into log form, so it'll be log base 0.96597 of 1/2 equals t. If we change it from exponential form to log form. And then we can just type that into our calculator. So we can do alpha window log base 0.96597 of 0.5. And that gives us 20.02 about. And that's in days. So that'd be when half the amount's remaining, so that's the half-life. Alright, the next problem says 20% of a reactive substance decays in 10 years. So we can go ahead and fill that out in our exponential equation. Whatever amount we start with, we want 20% less than that. So if we start with A, it'd be 0.8A. So we take 1A minus 0.2A to get that. That's 20% less. We don't know what B is, but we know this happens in 10 years. So we can solve for B now. Cancel A and do 0.8 to the 1/10 power, or the 10th root. And that gives you a B of 0.9779. And then you can just do 1 minus that value to find out what the rate is, which is negative 0.02067. So that's 2.2067%. Keep quite a few decimal places on that. That's how much it's decaying per year, because keep in mind that B is always 1 plus the R. In this case, our R is this value right here. or written as a percentage, decaying, or negative 2.206. But it says decay, so you can enter in a positive 2.206. We know it's decaying by that amount. Okay, the next problem then, under ideal conditions, certain bacteria population is known to double every 5 hours. So we can use our formula y equals a to b to the x. If it's going to double, then our b is 2. And it happens every 5 hours, so we put 5 here in the denominator. So here's our formula then. A is the starting amount, y is the final amount. Suppose the initial amount is 800, so we put 800 in for A. What's the size of the population after 15 hours? We plug in 15 for x right there, which gives us 6,400. After t hours, we just plug in the equation, 800 times 2 to the t over 5. Make sure this goes in parentheses right here. And then estimate the size of the population after 19 hours. We plug in 19 right here. And that gives us about 11,143.05. And that should be good. I'm not sure how many decimal places they want, but it should be close. You might have to add a couple more. And the last problem then gives us a cup of coffee, so we're using exponential. We start with 90 milligrams of coffee. Every hour, 12% is metabolized. So that'd be 1 minus 0.12 is our rate. Raised to the t power, which is our time in hours. That gives us the amount remaining. I'll use A for that. Or they want C of t, sorry. So there's our function, 90 times 0.88 raised to the t. You can go right here. And then how much caffeine is in the body after 4 hours? Just plug in 4 right there, and you'll get your answer. All right, hope this helps.